What I want to share with you today sits at an intersection that I think you'll find familiar: information theory, the philosophy of mind, and the question of what it actually means for a system to be intelligent. We've been working on a formal framework that started as an engineering problem. How do you know when an AI system is drifting from what it learned and ended up somewhere much more interesting? It ended up touching the same questions Wheeler was asking, the same questions you've been asking. So the title is deliberate: Information, Agency, AI, and the Mind, in that order, because that's the order in which the story unfolds. I want to start somewhere that might feel familiar. Wheeler spent the last decades of his career insisting that information is not a description of reality. It is constitutive of it. Every interaction is a binary choice, it from bit. Schneider's superpsychism takes this seriously as a physical hypothesis. If reality is computational at its foundation, then the fabric of space-time is generated by quantum computational steps. These are not peripheral ideas. They are attempts to answer the deepest question physics has left open. Why does the universe have the structure it does? And why does complexity arise within it? Our work begins from the same place. Physical interactions are sequences of choices, transitions between states. Each choice either converts uncertainty into information or information into uncertainty, with a bias toward the former. P measures the efficiency of that conversion. The central challenge in science is knowing what to measure and how that metric actually relates to the behavior of the system the theory is trying to explain. This presentation is about exactly those two things: what to measure about intelligent systems and how that measurement relates to their behavior. Wheeler and Schneider identified the theory. We are proposing a formal attempt to measure and implement it. Before we get to anything formal, I want to ground this in something intuitive. Information, in Shannon's sense, is not about content or meaning. It's about reduction of uncertainty. If I know the stock price today, how much does that reduce my uncertainty about the portfolio value tomorrow? That's information. The two circles you see here, S and S, represent any two states of a system, before and after. The arrow between them is the question: how much does knowing one tell you about the other? The Sudoku example on the right makes this concrete. The filled cells are the known state S. The empty cells are S. The more filled cells you have, the lower your uncertainty about what's left. Information is always relational. It only exists between states, never in isolation. That's the first important point. Now we add an agent, something that doesn't just observe states, but takes actions. A trader observing market conditions, choosing to buy or sell, and watching what happens to the portfolio. A doctor observing symptoms, prescribing a treatment, and tracking the patient's condition. What is that agent actually learning? It's learning the relationship between what it sees, what it does, and what results. Formally, given S and A, what is the probability of S? That's MISAS, the mutual information between the joint observation-action pair and the resulting outcome. And here's the key insight. Every AI model you've ever heard of, supervised learning, reinforcement learning, large language models, is fundamentally trying to learn this. The architectures differ enormously. The objective is the same. So what's the problem? During training, the spaces are fixed. The model sees a defined distribution of S, A, and S, and it gets very good at learning the relationships within that distribution. But when you deploy it, the world changes. New observations appear that were never in training. New outcomes emerge. The distributions shift, and the model has no way of knowing this is happening because it has no signal that measures its own informational coupling with the world. It keeps predicting as if nothing changed. The entropy histograms at the bottom tell the story visually. Training produces tight, structured distributions. Deployment produces something messier, broader, more uncertain. The model is operating in a different informational regime, and it doesn't know it. This is where P comes in. P is simply the ratio of shared information to total uncertainty in an interaction. Mutual information, given observation and actions. What is the outcome? In the numerator. How much of the outcome is explained by the joint observation and action? Observation's entropy plus action's entropy pulls outcome's entropy in the denominator, the total uncertainty across all three components. What P measures is not how much information there is, but how efficiently the interaction converts uncertainty into information. And crucially, P is a property of the interaction, not of the agent or the environment separately. You can't measure P by looking at the agent alone. You can't measure it by looking at the environment alone. It only exists in the relationship between them. This is why it's substrate independent. It doesn't matter whether the system is a robot, a language model, or a neural circuit. As long as you can define states and transitions, you can compute P. This slide makes a distinction I think is important and often missed. Every AI system predicts. That's not intelligence, that's pattern matching. Intelligence, in our framework, requires something more. It requires agency, the capacity to take actions that are not fully determined by observations, that causally influence outcomes, and that make the interaction directionally irreversible. And it requires something beyond learning, the capacity to monitor your own P and to adapt your scope, to change what you observe, what actions you take, what outcomes you pursue, in order to increase it. An AI that only learns MISAS triplets is doing the first step. An intelligent system monitors the ratio and adjusts the scope. That's the distinction between a very good lookup table and something that can generalize. And now, for the first time, we have a formal quantity that makes that distinction measurable and comparable across machines and humans. The chart here is the result that surprised us most. We computed P across 4 entirely different systems: quantum, classical, agentic, and linguistic. Same expression, different physics, and the bounds emerged consistently, not because we designed them to, but because the mathematics forced them. Classical systems cannot exceed P equals 1/2. Agentic systems settle around P equals 1/3. Quantum unitary systems reach P equals 1. These are not parameters we tuned. They are constraints the expression reveals. And that is precisely what elevates P from a useful metric to a physical one. A useful metric measures something. A physical constraint tells you what is possible, regardless of substrate, objective, or scale. That's the claim. So if P is a real physical property of interactions, can we engineer it? The information digital twin is our answer. The architecture is analogous to the thalamic cortical loop in the brain, and that analogy is deliberate, not decorative. The thalamus doesn't process raw sensory data. It regulates what reaches the cortex. It gates information based on relevance and context. The IDT does the same thing in the information dimension. It sits between the agent and the environment, receives the full triplet SAS from every interaction, computes the actual P, compares it against an expected P, and generates a deviation signal delta that feeds back into the agent's behavior. Over time, it builds a complete record of every SAS triplet the agent has encountered, what we call the information genome. That record captures not just what the agent has learned, but how informationally efficient each of its choices has been. It's the agent's informational history. The information genome is what makes this architecture scalable. Because P is a ratio, it scales naturally. You can compute it over a single interaction, over an agent's entire life cycle, or across a population of agents simultaneously, and the meaning stays consistent. The data you see here is real. P records from LLM dialogues on the left and from a robotic control system on the right. What you're looking at is the complete informational fingerprint of how these systems couple with their environments. Two systems with the same reward performance can have completely different information genomes, and those differences predict future behavior, identify failure modes, and enable a kind of governance that has nothing to do with opening the black box. We validated this across 3 very different settings. In robotic control, a half-cheetah agent with 43 state dimensions, P detected degradation in 89% of cases, compared to 44% for reward-based signals, and did so 4.4 times faster. In LLM dialogue, 100% perturbation detection across all frontier models and perturbation types, using only token frequency statistics with 0 access to model internals. In machine vision, 90% noise detection accuracy with 0 false positives. The common thread across all 3, P detects structural changes in information flow that precede observable failures. By the time the task performance degrades, P has already moved. This is what you want from a monitoring signal, not a post-mortem, but an early warning. This is where the engineering question and the philosophical question converge. The IDT architecture gives a system something no current AI has, a model of its own informational coupling with the world. It doesn't just predict outcomes, it tracks how well it is coupled to the process that generates those outcomes, and it corrects when that coupling degrades. That self-referential loop, compute P, compared to expected modulate behavior, is structurally analogous to what we'd expect from a system that is aware of itself interacting with its environment. We are not claiming this is consciousness. We are claiming it is a formal, measurable, substrate-independent experimental platform for asking the question rigorously. What we propose is to run this architecture in parallel on AI systems and biological neural systems, from fruit fly to mammals, and cross-validate. What we learn about P dynamics in AI informs what we look for in brains. What we find in brains informs how we design the next iteration of the architecture. The research question is not, what is consciousness? It is, what are the measurable informational and architectural conditions that must be present before consciousness can emerge? Everything we've shown so far, P, the IDT, the validation results, has been about measurement and regulation in spacetime. But there's a deeper claim underneath all of it that this slide makes explicit. The P optimization process, the continuous calculation, prediction, and correction of coupling efficiency, doesn't happen in spacetime. It happens in the information dimension. Spacetime is where we observe its consequences. The infogen is where those consequences are recorded. Think of it this way. Schneider proposes that spacetime emerges from prototime through decoherence. We are proposing something parallel. Physical informational objects, infogens, emerge from the ID process as its projection into spacetime. The process is in the information dimension. The record is in spacetime. This gives us 4 testable claims, one for each domain where that process operates. In AI, P optimization is the mechanism behind continuous learning and self-awareness. In neurology, real-time P fluctuations regulate biological behavior directly, manipulate P, behavior changes. In physics, if P changes precede physical behavior, then the information dimension is not describing physics, it is driving it. And in consciousness, if corticothalamic coherence tracks conscious state across species, then that loop is the P optimization process running in biological hardware. I want to end where we began. Not with a summary, not with a call to action, but with the single thought that started all of this. Physical interactions are sequences of choices, transitions between states. Each choice either converts uncertainty into information or information into uncertainty, with a bias towards the former. That's it. That's the seed. Everything you've seen today, P, the IDT, the infogen, the 4 research directions, the connection to prototime, every single piece of it is the unpacking of that one idea. Wheeler said it from bit. Schneider asked what that arena looks like. We asked, what does it measure, and how does that measurement change the system? If interactions are sequences of choices, and choices have a direction, then information is not a description of reality. It is its mechanism. And if that is true, then we are not studying AI or neuroscience or physics or consciousness separately. We are studying the same process in different substrates. That is the research program we are proposing here. Thank you.